been looking forward to using Avi's gavel. And I think we're actually going to have to get a better table because we have more gravitas with the sword. So anyway, Avi's in California, so I'm sitting in for him. And we've actually got a very interesting program as we start out with Zucker, who's at the CFA. And then we'll move on to James Owen from Imperial College London, Jason Wright from Penn State, and Bryan Terrazas from the University of Michigan. I think everybody knows the drill. So we'll get started with Catherine, large-scale galactic filaments, shock and shear in the Milky Way.
Okay. Thanks, Charles. Today I'm very excited to talk to you all about large-scale galactic filaments, shock and shear in the Milky Way. So I want to begin this talk by discussing what a large-scale galactic filament actually is. So large-scale galactic filaments are the tiny, tiny fraction of filaments in the Milky Way that we think form due to the large-scale gas dynamics of spiral galaxies. And so we see filaments all over the ISM, but these filaments usually exist on smaller scales, and they're formed due to more local forces. And so those filaments don't necessarily care where the gravitational midplane of the galaxy is, and they also don't care where the spiral potential wells of our galaxy are. But we think that large-scale galactic filaments actually do. And so, I think so. Is this a little bit better? And so what I'm showing you right here is a top-down view of the total column density of structures forming in a highly resolved section of the disk from the Smith et al. 2014 Milky Way simulations. And so I want to emphasize that this simulation only includes an imposed four-arm spiral potential and doesn't include anything else that might be important. So no local self-gravity, no magnetic fields, and no feedback. So this is only showing you the structures that are forming due to the imposed large-scale spiral potential. And so what you're finding is that there are two populations of large-scale galactic filaments that we see in this simulation. So the first population are shown in red, and those filaments are actually forming in the inner arm regions of the galaxy, and they're forming outside the imposed spiral potential due to galactic shear. So gas is sheared out in between the inner arms, and you get these very long, 200 to 300 parsec long structures in the inner arm regions. And so the second population of large-scale galactic filaments that we see are in blue, and these filaments are actually formed in the imposed spiral potential wells, so they're forming in the deepest points of these potential wells, and they're forming as gas falls into the potential well, it gets shocked and compressed, and you get these very transient but very dense elongated structures that are demarcating the spiral potential well of this galaxy. And so that's just your very brief 2-minute introduction into the title of this talk, but I want you to keep in mind this image as we go forward, and I discuss later in this talk our efforts to build an observational sample of large-scale galactic filaments that is worthy of comparison with this simulation and also more advanced simulations which include more detailed physics. And so one might ask why we started looking for large-scale galactic filaments in the first place. And it's a good question because we only actually started doing this in the last few years. And so essentially this whole avenue of research started with a very special discovery about an observed filament in our galaxy called Nessie. And so you can see Nessie here as this long wavy extinction feature. So it's so dense that it extincts light at mid-infrared wavelengths, and you get this very long infrared dark cloud. And so it was originally studied around 10 years ago for its high-mass star formation potential. But we're interested in Nessie not just for the high-mass stars it forms, but also for its very unique morphology, and also for its very unique position in our Milky Way. So essentially what Goodman et al. 2014 found a few years ago is not only Nessie, this 80 parsec long structure you see inside this box, but it's at least twice as long as originally claimed, and potentially as high as 5 times as long. And so you have a filament that's at least 160 parsecs, and potentially as high as 430 parsecs, while being less than a parsec wide. And so the question is, how do you form and maintain a structure that is this long and this skinny without large-scale galactic forces? And so if this is true, it would imply that Nessie has to lie in a very special place in our galaxy. And indeed, we find that it does. So if you analyze the 3D position of Nessie, you'll find that it actually lies exactly in the predicted location of the physical galactic midplane. And not only that, but it lies essentially at the predicted distance of a major spiral arm in the inner galaxy, the Scutum-Centaurus arm. And so the idea is Nessie could be one of the blue filaments I showed you in the previous slide. So it could be one of these filaments that are forming in the gravitational midplane of our galaxy and potentially tracing a part of the Milky Way spiral potential well for that arm. And so that was very exciting for us. And so as a result, over the last few years, our group here at Harvard and also groups around the world have devoted a lot of effort to finding more of these large-scale galactic filaments in our own Milky Way galaxy. And so as a result, we now have a sample of 50 of these structures known to exist in the Milky Way. And so that's great because we have higher numbers. But the issue is that all of these different groups use very different selection criteria. They use very different methodologies. They use very different data sets. And they compare to very different spiral arm models. And so that's an issue if you're trying to compare these systematically with the simulations, if you don't know how these filaments that these different groups extracted actually compare and relate to each other. And so what we did here at Harvard over the last year or two is we produced the first systematic analysis of the physical properties of all claimed large-scale galactic filaments in the literature. And so we took all of these discordant studies and we used the same data sets, we used the same observational pipeline, and we compared them to the same spiral arm models in order to produce a sample that was worthy of comparison systematically with these simulations. And so this is the figure that I like to show people when I try to emphasize the differences in what people have found. So essentially, each filament in each of these different panels show different catalogs of large-scale galactic filaments. And each filament is represented as a rectangle with the same length and width that I measure uniformly across the sample, and also the same height above or below the galactic plane, and the same 2D orientation with respect to the galactic plane. So all of these filaments were analyzed using the same pipeline. And so you can see NESI is right here. And then this sample over to the left, these are the NESI analogs that our group found a few years ago. And we called these filaments the Milky Way bone sample because we think they could have potential for tracing out the major structural skeletal features of our galaxy. So either the spiral potential wells or these very prominent inner arm features that form in between the spiral potential wells. And so these are the NESI analogs. They're very long and skinny. They're close to the galactic midplane, and they're also parallel to the galactic midplane. But we see a lot of other structures that are demonstrably different than NESI. So some structures that people have found are a little bit larger, perhaps, but they're also a lot wider, and they tend to be lower column density. Some structures reproduce NESI's morphology, but they're not exactly parallel to the galactic plane, and they're also a little bit higher off the plane, which begs the question of how do you actually form these structures if not inside the galactic plane? Or a better question is how do you actually get them up there? And so the goal of our study is to understand how these different populations of large-scale galactic filaments form in our galaxy. Do they have the same origins? Do they have the same evolutionary histories? Do they have the same destructive processes? Do some categories evolve into other categories? Do some categories, for instance, preferentially trace the spiral arms and form via this compression and shock as you fall into the spiral potential well? Do other categories perhaps form preferentially via shear in the inner arm regions? And so we want to understand all of these structures in the relationship to galactic structure, and we want to do that using a comparison, a one-to-one comparison with the simulations. And so having a complete set of physical properties for all of these structures is obviously very nice, but we need more than this. We actually have to know where these structures lie with respect to predicted models for spiral arms in the Milky Way. And so this is what I'm showing you right here. Ideally, we'd want to compare the location of these filaments and the location of predicted spiral arms in the Milky Way in position space. But finding distances to structures in our galaxy is very difficult. And so instead, we look in position velocity space. And so we usually use CO, molecular gas, as a tracer of the underlying molecular hydrogen. And so what I'm showing you right now is two 2D projections of this 3D position velocity cube of molecular gas in the galaxy. And so the top panel is showing you velocity on the y-axis, longitude on the x-axis, and then in the bottom panel you have latitude on the y-axis and longitude on the x-axis. And so what I've done is I've overlaid the predicted positions of spiral arms, and I've also overlaid the predicted positions of these large-scale galactic filaments that I've again calculated uniformly across the sample using the same observational pipeline. And so I just want to zoom in on this top panel so you can see everything in a little bit more detail. And so again, these black tracks, these are models for predicted spiral arms in our galaxy. And they come from actually Tom Dame here at the CFA and published in Mark Reed's 2016 paper. So these are the brainchild of CFA scientists. And what you'll see is that these filaments show a wide variety of orientations with respect to the spiral arms. So some filaments, like this NESI analog here, filament 5, it lies along the spiral arm trace. Others lie along but slightly offset. Others lie completely perpendicular to predicted positions of arms and also in between major spiral arms in the galaxy. And so the ultimate goal here is to be able to refine our understanding of the spiral arms. But in order to do that, you have a little bit of a circular logic. So you want to find which filaments trace the arms, but you also have to use the arms in order to have a first guess at which filaments might do that. And so the end goal here is to take the complete set of observed properties of large-scale galactic filaments in our galaxy, take the predicted position of these filaments by comparing them to spiral arm models in our galaxy, and then do the same exact thing in the simulations. Apply the same observational pipeline and develop the same set of physical properties, and also reproduce things like this LV diagram, using synthetic CO from our synthetic Milky Way galaxies that are forming these filaments. And so that's what we're planning to do in the next few years. And so that's all I have for you today. And I thank you for your time, and I'd welcome any questions. Thanks. Yep.
If you have charts in the gaseous medium there, usually spectroscopic top features, you or anybody else looking for them?
Yes, so that's a really great question. And so the issue is that we only have high spectral resolution observations for a single filament so far. And so we're limited in that sense, but it is something that we're going to actively be working on in the future. The challenge from the simulations is that, so our galaxy includes CO formation and destruction, includes hydrogen chemistry, but we can't actually form any of these spectroscopic tracers in the simulations at this point. And so that would mostly be observationally driven, I think, but I'm welcome to ideas if you have a better way to do that.
It's very impressive, this sort of 300 to 1 aspect ratio indeed.
Yep.
But you were asking sort of what sustains these filaments, and when I look at simulations, I'm just not so sure anything does. I mean, they're very short-lived sometimes when you look at these disks, right?
Mm-hmm.
So is there any chance that they're just sort of random, like very short-lived?
So I agree with you that they're short-lived, but I wouldn't agree that they're random. And so we expect all of the features in this galaxy to be very transient. So we only expect them to survive on several million-year timescales. So they'll either be destroyed by galactic shear, they'll either form stars and they'll get broken up internally, and so on and so forth. But even if this feature, for instance, only exists for 4 million years in the galaxy, you're constantly forming and destroying things that could demarcate the spiral potential well. And so even though they're being destroyed rapidly, they're still forming in special locations, and so we still think they might be useful for understanding our own Milky Way.
Do you have any handle on the distances?
Yes and no. So we have a handle on the distances, but whether they're accurate enough to actually give us the 3D orientation of these filaments is a different story. And so we have kinematic distances to all of these filaments, but of course kinematic distances are very unreliable, and you don't have enough precision to actually place one end of the filament at a different distance than the other end, which would be great because then we could get the true extent of these filaments. But one of the things that we're working on, that I'm working on with Doug Finkbeiner, is trying to find dust-based distances to these structures. And so I have a whole other part of my life where I try to find distances to things. And so that's, again, our top priority over the next few years in order to build up a better model of the arms and also the filaments that we think form along and between them.
So comparing like the bones to the molecular filaments, are
Yeah.
there differences like in the star formation and those things? Like could the molecular filaments be more evolved with more stars so that that could pop up gaps possibly?
Yeah, so it's a good question. So I'm not particularly focused on the star formation properties, but there have been studies that have been done to look at that. But they're not really looking, so essentially other studies have compared apples to oranges, so they're not really looking at the same structures uniformly like we have. But our current idea for how these giant molecular filaments form, is that they might form in the inner arm regions. And some speculate that the giant molecular filaments might actually evolve into these bone-like structures in the arms as they get more and more evolved, and then they fall into the potential well and they get very dense and have very high molecular gas fractions. So that's just one conjecture. But star formation is definitely something that is to be explored further as well.
Perfect. Right, thanks very much. So yes, I'm going to talk about misaligned circumbinary disks, and like many problems in the protoplanetary disk field, which this is essentially in, it started with a recent observation, right? So this is a new observation, new-ish, 2014, of a protoplanetary disk, and I'll go into more details of why it's a binary system. So this is not an ALMA image. So many of the amazing things we've seen have come out of ALMA, but this is a different type of high-resolution image. This is a near-infrared scattered light image that's come out of Sphere and GPI over the last few years. So the important distinction between ALMA observations and these near-infrared scattered light observations is we're not actually probing the bulk of the material in the disk. The way the observations are constructed is to remove the star. What we're looking for is for polarized light from scattering off the disk's surface, right? So we're not probing the bulk of the material in the disk. What these observations are actually probing is parts of the disk that can see the star and have light scattered off towards the observers. So these bright regions obviously subtend a large solid angle to the star, and you can get lots of scattering, but these regions where you have absent emission is not from the fact that there's no material here, but they're probably shadowed from the star, right? So the mystery is, as the mystery is with many of these protoplanetary disk observations, is none of the observations look like a disk, right? What on earth is going on to give you a emission pattern like this, where you have strong emission here and shadowing here? So it was worked out that perhaps the way to explain this type of emission structure is by shadowing portions of the disk. If you shadow it, then the disk can't see the star, and you can't get any scattered light off the disk. So if you have an outer disk with a gap, and then you have an inner disk that is misaligned to the outer disk itself, then the fact that these two are misaligned means that this inner disk can shadow regions of the outer disk, and these shadows and bright parts can then give rise to this emission pattern. So you have, in this model, you have essentially two free parameters. You have the inclination of the inner disk with respect to the outer disk, and you also have the position angle of the disk on the sky. So if you take this model and you create some radiative transfer simulations to compare to the observation, and you step through these various parameters, you can see this quite nicely by eye, that this kind of observational pattern here is quite nicely explained by an inner disk. These are misalignments between the inner and outer disk in degrees, where the inner disk is highly misaligned with respect to the outer disk, right? So this is actually it's a high mass ratio circumbinary disk, so it has an observed companion inside this cavity between the inner and outer disk. The orbit is very poorly unconstrained, so I'll come back to that at the end, and one suggestion of what this orbit might be. The other very interesting thing about this companion in the disk is it has a H-alpha emission as well that's detected, so it's accreting from the disk itself. So this companion is truly interacting with this circumbinary disk. So the question I'm going to posit in this very short talk is, where on earth might this misalignment come from? Can we think of any mechanism that could take a flat disk setup here and give you a large misalignment that we observe today. So this is the setup we're going to consider. We're going to have an outer disk which has a high mass ratio companion in it, and then an inner disk. And think of mechanisms that might be able to misalign this system. Right, so if it's perfectly aligned, you have to conserve angular momentum in the vertical direction with respect to the disk. There is no way to misalign this system if it starts off perfectly aligned. But there are many, many mechanisms that could give you a very, very tiny misalignment. Right, there might be some turbulence in the disk that might perturb the companion. Slightly, you might have an interaction with another star in your forming cluster that can perturb it. So if you imagine you have a very slight misalignment that can come from any of these processes, then these outer disks, this companion, and this inner disk are going to apply torques to each other. Right? So the outer disk has most of the angular momentum, so it just stays fixed in space, but it applies a torque to the companion and causes the companion to precess around its angular momentum vector. And then finally, the companion applies a torque to the inner disk and causes the inner disk to precess around its angular momentum vector. So the question you should have is, what is the evolution of this precession, and is there any evolution we can construct that can take a very system that's very, very close to alignment and misalign it by 70 degrees, for example? So the way to understand this is not to consider it in the lab frame, but to transform into a frame that is precessing with the companion. So in this frame, the companion's orbit basically stays fixed in space, and now the outer disk is precessing around the companion. And the question is, what on earth a vector is the inner disk precessing around? Right? And you can get this with simple vector calculus. So we were in a frame where the inner disk was precessing around the companion, and now we've transformed into a frame where we're processing with the companion. So simple vector calculus gives you that the precession frequency times the vector at which you're processing around is given by this formula. So if you're in the region where the inner disk precession rate is much, much higher than the precession of the companion, then we can just throw away this term and you get what you expect, that you're just precessing around the companion again. The outer disk is not moving in this frame. If you switch to the opposite limit, then you get the opposite effect and you're just precessing around the outer disk again. Now the interesting thing is what happens when these two precession frequencies become comparable. When they become comparable, now the precession frequency, vector that the angular momentum vector you're precessing around is now proportional to the companion's angular momentum vector minus the angular momentum vector of the outer disk. So if we now consider that we're taking the minus of the outer disk and adding to it the companion, then you have two vectors that are very, very aligned, right? If you take the difference of two vectors that are almost completely aligned, you end up with a new vector that is orthogonal to those two vectors. So now you're processing around a vector that is basically orthogonal to our starting vectors. So if you can sit in this resonance where you have an inner disk precession frequency and companion precession frequency that are identical, you can process significantly far around this new vector such that then you become highly misaligned. So this is what I suspect might be happening. You can write down a resonance criterion that depends on the mass of the companion, the mass of the outer disk, and the sizes of the disks and the position of the companion. And the interesting thing is, in a real disk, all these things evolve, right? So the mass of the companion is evolving due to accretion. It's accreting from the disk. The position of the companion and the sizes of the inner and outer disk are evolving because the companion is migrating through the disk. And then finally, the outer disk, the mass in the outer disk is evolving because the disk is accreting. So you can start off with a disk that is far away from this resonance, and then you can let the disk evolve, and it will hit one of these resonances, and you will undergo a very strong misalignment. So starting off with very, very small misalignments, you let the disk evolve, suddenly you hit one of these, this resonance, and the misalignment becomes very, very large. So you end up with a large misalignment. In this case, it goes up to 90 degrees between the companion and the inner disk. the important thing to remember is in everything, the companion is still just processing around the outer disk, so its misalignment doesn't change. So the companion and the outer disk will always remain misaligned. So in this specific system, since the orbit of the companion is unconstrained, or the orbital inclination is observationally unconstrained, given enough time, we might suggest that it would be, to confirm this, you would have to have the companion and the outer disk align. The other nice thing about this system, HD 142527, is if you take that resonance criterion and plug in everything we know observationally, it seems to work quite nicely. That resonance criterion is matched by the mass in the outer disk, which we can measure from observations, the mass of the companion, which we can measure from the observations, the radius, inner radius of the disk we can measure from the observations. So everything quite nicely works in this one system. So there are other misaligned protoplanetary disks which we don't know have a companion in it. So the prediction would be that these do have quite massive companions, not planetary mass companions, but brown dwarf or stellar mass companions. And the companion should always lie in the same orbital plane as the outer disk. Thank you very much. That is an incredibly good question to which I don't think we have a good answer yet. So it's plausible you could trigger Kozai-Lidov oscillations, but that depends on having a massive enough disk and a lower mass companion.
You're looking at the outer disk.
Yeah.
If you took that outer disk and you replaced it by a star, so you now have a three-body system,
Yeah.
would some of these same considerations work?
Exactly. Yeah, so that is exactly where the idea for this came from, that these kind of dynamical secular precession resonances have been studied in three-body stellar systems and three-body planetary and moon systems. So all we did is, in noticing this, is realize the connection between the planetary and stellar dynamic system and the dynamics that might be going on in these disks.
This seems totally crazy to me because, I mean, even if you have just a little bit of viscosity in the inner disk, shouldn't it just align with the binary? Wouldn't it just be simpler to think that the binary is misaligned?
Yeah, so this system will realign due to viscosity. So what is different to other types of accretion disks where the viscosity is high and the pressure support is low that you might get around black holes, say, is that the bending waves in the disk do not propagate viscously. They propagate like sound waves. So, and that's much, much faster than any of this timescales we're talking about. So the people have studied this bending wave propagation in these protoplanetary disks where the viscosity is low and the pressure support is high, and find that tends to force the disk to behave like a rigid plate. So that's the first bit, and the second bit is that viscosity, so accretion from the outer disk, will have to realign the inner disk over the viscous timescale on the outer disk as material flows from the outer disk into the inner disk. You have to conserve that outer disk's angular momentum into the new orbital plane, right? So they should realign on a million-year timescale. Does that answer your question?
I don't know.
Okay, one more question.
Do you have an estimate of the mass of material required to produce the scattering you're seeing? Forget the underlying physics. How much mass are you talking about?
To produce, it's a tiny amount of mass to produce the scattering.
I'm wondering, I mean, could this have an alternate explanation of what you're seeing are rains that are produced through collisions of Kuiper belt objects?
That is plausible if we didn't also have the ALMA observations, which tell us that there's a lot of millimeter dust and gas that is also aligned with this system. So we know it's true. The outer disk is truly a gaseous, massive disk. If you combine this with the ALMA observations, if we didn't have the ALMA observations, that could be exactly right.
Okay, well, thank you very much.
Cheers.
All right, I'm going to start this talk by asking you a question. It's a 5 multiple choice question. You're going to answer by holding up a fist. Answer 1, 2, 3, 4, or 5. This is a little history quiz for you all. And so the question is, who provided the first observational proof that the Earth moves around the sun? I'm still not convinced myself. All right, here we go. 1, 2, 3. You got to vote. I'm sorry, you have to vote. Is this the rule? Okay, let's get into this. So, of course, it used to be not at all obvious that the Earth goes around the sun. Ptolemy and the Almagest, the astronomy text for over 1,000 years in Europe, said that the Earth sat at the center of the universe and didn't move at all. And of course, it was Copernicus who was the first one to put forward an equivalently good model of describing the motions of the planets through the sky by having the Earth orbit the sun instead. A lot of people didn't like the idea of a moving Earth, but did like Copernicus's model. And the person who maybe took that philosophy to an extreme was Tycho, who just took Copernicus's model and did a reference shift and put the Earth at the middle. So the sun and moon went around the Earth and everything else went around the sun. Observationally identical to Copernicus's model, but didn't have the Earth going anywhere. So the proof that either Tycho or Copernicus was right was first offered by Galileo, who saw the phases of Venus, showing that Venus does indeed orbit the sun. But Tycho, being clever, pointed out that didn't mean it was necessarily the Earth that was going around the sun. So we still didn't have that the Earth was moving. And so Tycho's model still in principle was valid. Nonetheless, most people were persuaded by Galileo's observations and how well Copernicus's system worked. And so it's said that when Galileo was before the Inquisition and he had to recant his heliocentric positions towards the end of his life, supposedly he muttered under his breath, a dangerous thing to do in front of the Inquisition, Eppur si muove, apologies for my Italian, and yet it moves, that he had not truly abandoned his beliefs. And this story actually goes back to probably his own lifetime. This is a painting of Galileo painted shortly after his death. It shows him in captivity awaiting trial. And you can't see it here, but apparently up in the corner written on the chalkboard are those words. So we know that this story about him saying this goes back to his own lifetime. But he, of course, didn't have proof that it was the Earth moving. He only had proof that Venus went around the sun. The ultimate proof, everyone presumed, would come from measurement of the geometric parallax. And so for centuries, people made observations of the positions of stars, trying to see the nearby ones move against the background ones to show that the Earth was going around the sun. And so this is an absolute measurement. I know the Big Dipper's not in that direction. This is just a schematic. But, you want to see the Earth go from one side to the other, and that would finally prove it. The problem is this is really, really hard to do by eye. We know, even with a telescope, we know today, and they had a good sense, that the effect was very small. It's less than an arc second. That's less than the seeing. You can't use binary stars because they're almost always at the same distance, so they share a parallax, so you can't do it differentially. There was no way to record a stellar image, so you had to do this by eye with a telescope. How are you going to do this? So the solution was to find a way to measure positions with respect to some absolute reference on the sky. And so people did this a lot. They found absolute positions on the sky and measured positions. But the results were really confusing and inconsistent and larger than expected, and there was a lot of argument in the literature what was going on. It was Bradley that finally put it all together. So this is a schematic of his zenith sector. It uses a plumb line to find the local gravity vector to ensure that the telescope is pointed at the true zenith. He would then watch zenith crossing stars go by and determine how close north-south they were to the zenith. Now, he couldn't make any east-west measurements because that would require timing, and he didn't have a good enough clock to do the timing. But he could measure how far north or south. So this is a stable instrument, stable pointing, and he's measuring by eye when bright stars cross the zenith. So it's very clever. And so what he expected to see is he's measuring north-south deflection. So for stars that are crossing the meridian at midnight in December, what he was expecting is to see the maximum east-west deflection in September and the equinoxes, and to see the maximum north-south deflection in December, because the parallax always moves stars towards the sun. And when you're at midnight on the meridian, the sun is at the anti-meridian, so it's a north-south deflection. And that's not what he found. What he found is very large variations, and he found them maximized in March and September, which did not make any sense. So he puzzled over this. A lot of people had similar observations, didn't seem to make any sense, and he finally published it in Philosophical Transactions. This is a great read. I recommend looking it up and reading it. It's just a lot of fun. He walks through how he built the thing, how he made the measurements, how they made no sense, how he puzzled over it, and finally he figured out what was going on. And what was going on is what today we call the aberration of starlight. So his classical explanation is here, and he's got his little triangle, and this is what Wikipedia tells you. It's basically the same diagram, just a different reference frame. But the idea that I will tell my Astro 101 students is you've got a bucket, and you're on the back of a pickup truck, and it's raining straight down. And if the truck's not moving, you point the bucket straight up, and it collects raindrops hitting the bottom. But if the truck is moving, then raindrops are going to hit the side. If you want them to hit the bottom of the bucket, you've got to tip the bucket in the direction of the truck's motion to get them to go straight down the tube. And so as long as you have a particle picture of light and you don't worry too much about reference frames because they didn't have relativity yet, it makes sense that you should point the bucket in the direction that the Earth is moving. So your light bucket doesn't go north-south in December, it goes in the direction of Earth's motion. So in December, it was all east-west deflection, which he could not measure. And then in September and March is when he got the maximum deflection. And so he boasts a bit at the end of this wonderful little article, there appearing, therefore, after all, no sensible parallax in the fixed stars. The anti-Copernicans have still room on that account. So he hasn't found the parallax, which is what he was after. But he found something much better. They have, if they please, a much greater objection against the hypothesis, which I've explained, by denying the progressive motion of light as well as that of the Earth. So now they have to deny both that the Earth moves and that light moves at finite speed, which was clever. Interestingly, this proof that the Earth is moving is much bigger effect than 1 degree, or 1 arc second. It's 30 arc seconds. It's huge. And as far as ADS is concerned, it's only been cited twice. Once by me and once by Gerard Van Belle. So you'd think this would be easy to do. 30 arc seconds is easy, right? I mean, that's just pointing. Every telescope pointing model has it built in. We don't even think about it. But it's actually surprisingly difficult to measure in an absolute sense because we rarely trust absolute pointing. Radio telescopes do, but optical telescopes usually don't. It also affects all the stars in a region of the sky, so you have to have an absolute reference frame locally to make it work. And I thought, gosh, there's got to be an easy way to do this with undergraduates. And you need an absolute reference. So I thought, can you use like the corner of a nearby building or something like that? And then I realized there is in the sky an absolute reference you can easily find with nothing but a camera. In fact, you don't even need a telescope to find it. And it's the North Celestial Pole. You can easily find it by making star trails. And star trails will always orbit the true North Celestial Poles. And it doesn't matter what aberration is doing to the apparent position of the stars. Whatever they are, they will go around the North Celestial Pole. And so in principle, what you could do is take star trails with a camera, measure the center of the star trails, and then ask, if that were a star at that position, what would the star's coordinates be with respect to the other stars? And this is what you get. So this is a little funny. The loops that you're seeing are the aberration of starlight once a year. So in 2000, the green line with time, the loop around the North Celestial Pole was in 2000. And then it loops once a year, and it slowly drifts off to the east, and that's the precession of Earth's pole. Because this thing this absolute position is drifting on you. There's also the nutation of the Earth every 11 years due to the moon. But this is something that you could do with any old camera. A telescope would help because you could zoom in and get a very precise position of the center of the star trails. So it would be a lot of fun, I think, for undergraduates to point at the North Celestial Pole. You turn off tracking on your telescope. You take images. You stack them. You find the pixel at the center of those trails. Use the astrometric solution of any of the individual images to deduce the coordinates of the North Celestial Pole. And then you follow it. You'll have to do it for a couple of years to take out the precession. But if you were to do this, you would prove the Earth moves with a camera. That's all you need. You would measure the velocity of the Earth in units of the speed of light. You would measure the AU in light years. And you'd also get the rate of the precession of the equinoxes while you were at it. And all you need is a camera. You don't need anything else except that. So anyway, I published this up as a research note of the AAS. I think it would be cool to try sometime. I've been meaning to try this for years, and I just never got around to it. So instead, I published it out. And the answers to the quiz are right here. There you go. Thanks. Because there's a lot of things that are fun to do, and it just never seemed important enough to stay out all night and do star trails. Non-standard image analysis, I mean, you'd have to write, how do you find the center? And I always worry, is the telescope going to creep on me through the night? Am I going to have to take the creep out? Is there going to be differential refraction? So I'll have to chop between two colors. I don't even know if the building is that stable. Does wind tip my building? I just don't know if it's going to work, and so I just worry about everything that would eat up all my time. And someone I hope will take it up, and it'd be very cool, I think, for some senior astronomy majors to prove that the Earth moves all by themselves and measure the AU and all of that stuff with nothing but a camera. Anyway, it seems very didactic to me. So, anyway. But it's quite a puzzle to make that chart that I made. It's a real mental exercise to figure out where the center of star trails is in ICRS coordinates. All right.
Sounds like a good topic for a freshman seminar. Thank you very much.
All right. I'll give you that, and then I'll give you my mic. Yes, thanks. Thank you.
There's also this guy. This guy. It's on the one that's first.
Okay, cool. Great.
Bryan Terrazas from Michigan. Black hole galaxy scaling array. Physics remains the
Yes, hello. So I'm going to be talking about my research, which deals with how black holes fit into this picture of galaxies here that I've shown. This is a mosaic of SDSS galaxies, and I really want to understand how black holes influence the star formation properties that you see here, the diversity of star formation properties from star forming all the way down to quiescence. So to do that, I want to kind of start with an idea of a galaxy that and its star formation properties and how it comes to be star forming. So here I'm going to be talking about galaxies with stellar masses about 10 to the 10 solar masses, and at the centers of their dark matter halos. Not satellites, because that goes through other processes that affected star formation in different ways. So a central galaxy has a large reservoir of halo gas around it that has the potential to cool, condense, fall into the center, into a disk, and finally form stars that we see with our telescopes. Those stars form a feedback mechanism, which causes heating of the gas in order to regulate its amount of cooling from the gas halo, in order to form a regulatory cycle that we see as the main sequence of star formation. And so quiescence is then the disruption of this regulatory cycle between star formation and stellar feedback and the cooling that's coming onto the galaxy. And the question is, and also for long-term quiescence, we really need to prevent the reaccretion from happening continuously because this halo is not going anywhere. It still wants to accrete down into the galaxy and form stars. And so the question is, do we see this kind of disruption in observations? And the answer is absolutely. We see it in all these beautiful X-ray images from Chandra, and the radio on top of it shows the black hole producing these cavities into the hot X-ray gas around galaxies. And these are at very large scales around the galaxy. And so you're really seeing the black hole affecting the way that the galaxy behaves, the gas behaves around the galaxy, and potentially producing quiescence in the galaxy. So, a really useful way to look at black hole feedback in galaxies is looking at this three-dimensional parameter space. And it's a very simplistic picture. I want to warn you about that. But it's a very useful picture, and I hope to show you that. So here, the general gist is that the stellar mass is going to correlate with the halo mass, and that's going to correlate with the gas halo mass as well. And the more gas you have around the galaxy, the more potential you have for that gas to cool. So it's going to give you an idea of the total cooling that would be happening in the absence of any kind of feedback mechanisms. The black hole mass is going to give you an idea of the total accretion that happens onto the black hole, which is going to give you a sense of the energy from feedback that the black hole is giving off. And finally, the specific star formation rate is going to give you a sense of the distance, it's going to give you the distance from the star forming main sequence, or in other words, the degree of quiescence that galaxy is exhibiting. So in other words, it's going to give you the net cooling that happens as a result of the battle between the total cooling that wants to happen in the halo and the heating coming from the black hole. And so where galaxies lie in this three-dimensional space is actually going to be a really interesting problem to try and understand. So let's do it. Here I have a sample of galaxies with directly measured black hole masses. So I chose dynamical directly measured black hole masses because those are the best possible data that we can get for black hole masses, and I really didn't want to plot the stellar mass. So these two things are two independent measurements, right? So the black hole mass and stellar mass. So here I plot the black hole mass-stellar mass relation for these galaxies. I choose central galaxies only, so that reduces my sample from about 150 today, probably a little bit more now, down to 91 galaxies, including our own Milky Way. And what we see is a general positive correlation with a large scatter. And I'll get back to the scatter, but I want to show you that at a given stellar mass, you can have a scatter of about 2 orders of magnitude in black hole mass. This is quite interesting, actually, because if you color these points based on their star formation rates, and I've measured the star formation rates, and you can make the cut where the star forming main sequence is, and I'll color the galaxies on the star forming main sequence blue, and those that are quiescent or off the main sequence red. And if you do that, then you see this, where galaxies that are quiescent host more massive black holes than galaxies that are star forming. And if you just take 2 galaxies from this, then you can see that two galaxies have the same stellar mass, and yet they have different black hole masses, and you can see that they have very different properties in terms of one is a star-forming disky galaxy, and the other one is red, dead elliptical. And so, in order to understand this physically and move past this kind of empirical picture, we really need to go into the models. And so here, I show the observations on the left, and then the models that I'm comparing to on the right, in this black hole mass, stellar mass space. And what's really nice about the black hole mass, stellar mass space, in the fact that it's, one, it's simple to understand, and two, that models have these parameters available to them. And so I really can't get into the details of each of these models. There are 4 very complex models. But I want to impress on you one thing that I'm going to move on from pretty quickly and get back to at the end of the talk, is that all of these models produce very different distributions of black hole mass, stellar mass relations compared to the observations and compared with each other. All right, but I want to really focus on the qualitative comparison between these models and observations, in the sense that in the observations, you see a clear separation between star-forming and quiescent galaxies, in that the star-forming and quiescent galaxies lie in distinct parts of this plane in observations. In the models, this doesn't always happen. So let's go a little bit backwards. So for galaxy S, this implements quiescence through a halo mass threshold. So as soon as it goes above a halo mass threshold, galaxies quench. And since the black hole doesn't have anything to do with causing quiescence, but rather just maintaining it, there's not really a correlation between black hole mass and the star-forming properties of the galaxies. And you see an overlap in red and blue points here. For Eagle, this is a model that uses short intermittent bursts of feedback to throw the gas out of the galaxy, thereby stopping any kind of star formation. The thing is that they're short and intermittent bursts. So as soon as that short intermittent burst stops, the gas can cool, come back into the galaxy, and start forming stars again. Hence, you can get galaxies with very massive black holes, and yet they're continuing to form stars. This is in disagreement with the observational results I present here. For illustrious and L galaxies, they provide more of a permanent shut-off of star formation as soon as you start getting black hole feedback to be effective. And here, I'm showing that these observational results can give you a very decisive observational diagnostic test for galaxy formation models. And for these galaxy formation models that I show here, I show that effective, long-lived black hole feedback really works to replicate the qualitative feature that quiescent galaxies and star-forming galaxies lie in distinct parts of this plane. All right, so going back to the observations, I also want to note that there's a really interesting behavior for the boundary between between quiescent and star-forming galaxies, in the sense that the black hole mass isn't a constant there; it's actually a slope, and that slope is about 1, meaning that line there is giving you a line of constant black hole mass stellar mass ratio. And so actually, instead of coloring these galaxies by blue or red, we can actually look at the star formation rates of these galaxies individually as their values, as we have their values. So if we do that, then another way of showing the plane here that I've shown you before is by looking at this plane, where I show that the specific star formation rate is a smoothly decreasing function of the black hole mass stellar mass ratio. And this is giving you a sense that the specific star formation rate, or the net cooling, or the degree of quiescence that a galaxy is exhibiting, is a smoothly decreasing function of this kind of ratio between the heating and the cooling that's happening in the galaxy. And so currently I'm working on illustrious TNG, a model that has been formed here at ITC, along with MPIA. And I really wanted to understand how illustrious TNG compares in terms of these two kind of planes. So here, again, I can't really go into the model details very much, but I wanted to show the results. So here's the black hole mass stellar mass relation for illustrious TNG, and you can see a clear separation between red and blue points in qualitative agreement with our observations. But the thing is that the black hole mass threshold at which quiescent galaxies and star-forming galaxies live is actually flat on this plane. So it's a black hole mass threshold, and it doesn't depend on stellar mass. And so if we look at the specific star formation rate versus black hole mass plane, then we see that galaxies that are below this threshold mass are star-forming, and galaxies above are quiescent. In fact, they're all pretty much with a star formation rate of 0, so these are all upper limits here. And this step function, if we compare it to observations, is not really seen in my data. So here is just black hole mass again. And then you also see that the black hole mass stellar mass relation is actually very, very tight compared to the observations as well. And so this gives you a kind of idea of how you can compare models and these kinds of observational diagnostics. And so I kind of want to leave you with 3 points to take away, if you take away anything from this talk. One is that quiescence correlates with black hole mass. And 2 is that the scatter in the black hole mass stellar mass relation really does matter. Because the scatter between black hole mass and stellar mass tells you that the ratio between black hole mass and stellar mass changes at the same redshift. And that ratio between black hole mass and stellar mass is going to give you information about the specific star formation rate or the degree of quiescence that you have in your galaxy. And finally, I want to end with looking at these 5 different models that I've tried to fit into this 10-minute talk. And I want to impress upon you the differences between the black hole stellar mass relations here. They produce very different results, and yet they all use black hole feedback in some way or another. And I think, they don't just differ in terms of where their red and blue points lie, but also in their normalizations, their scatters, their slopes, etc. And so I think this offers us a wonderful opportunity to start looking forward to new models, to look back into these models and trying to improve them, and try and look at how we can get them to better match what we've seen in the real universe. So thanks.
Usually there are galaxies that weigh
bottom left of the diagram here.
You run out of points.
Oh yeah, absolutely. So this is observational bias. So all these points we've been accumulating slowly throughout the years since the first black hole mass measurements back in 1998 really with Gregorian. So you're slowly accumulating these black hole masses, and these black hole masses are gotten through a different variety of measuring techniques for dynamical mass measurements, and some of them are biased towards measuring active galaxies, all of them are biased towards measuring close galaxies, and some of them are biased towards measuring quiescent galaxies or galaxies with gas. And so this is an accumulation of all the black hole masses that we have that is a biased sample. In the end, this is the best thing that we can do, and this is the best that we can do currently. But the fact that we have galaxies that span a range of 4 orders of magnitude in black hole mass, and span a range of 2 orders of magnitude in stellar mass, and all the way from the star-forming sequence down to completely quiescent galaxies, shows you that these are consistent of not only ellipticals but spirals and different kinds of morphologies in different environments. These are BCGs, these are isolated galaxies, group galaxies, and it's showing you that they correlate in some way on this plane, which is remarkable, I think, to me. So.
Oh, yeah, it was kind of got into it. So there is a separation in the methods used to measure black hole mass between the red ones and the blue ones. How much does that worry you?
Yeah, no, this it'd be really wonderful to get a better and more complete sample. But again, these galaxies are extremely diverse, and I think it's very strange to get out this kind of relationship between these 3 parameters across such a large range of a parameter space in terms of their values. And so yeah, I think we really need to. So I'm keeping up with the black hole mass measurements that are coming out and trying to see if they match these kind of things. And so far it's all fitting in. So we'll see. We really need to get a better, more representative sample. Absolutely. Yes.
In the top left diagram, it's very nice, very nice. But then you drew a line with slope 1.
Yes.
Carefully putting all the red points to above. It isn't obvious that's the right fit to me. Could be, but it could be just the 2 relations are just offset from one another by a constant, and you have a scatter in both.
Right. So the thing is that this is
and then it's a steeper slope again.
So again, if you take the slope of 1, that's a constant black hole mass stellar mass ratio. If you plot the specific star formation rate against the black hole mass stellar mass ratio here, then you see a continuous, smoothly declining function. So they don't seem to be 2 separate populations, but rather make up a plane in that space there and here. So it seems to be quite continuous.
In the beginning, you drew a cartoon of the 3D picture. So,
yes.
Do you ever look at this?
Yes, absolutely. So that's how I found this. It's super cool. So I actually found this through looking at the 3D and moving it around and saying, whoa, in this space, like I have this, it just all falls into this plane. So it's super interesting. Yeah, that's how I do it.
Now we're done.
Thank you.
Hi, James. Dan. Nice to meet you. I work on circumbinary data for this and actually I was really curious too, just small things. I remember a long time ago, I don't know if you ever looked at Chris Nixon and Andrew King's papers on Misaligned. But before I think they ever looked into that, they had this circumbinary black hole paper where they did 2D SPH simulations. And they never explained it, but if you look at those pictures, they're mini disks, meaning circumbinary disks and 2 mini disks, are actually misaligned. And they start from an aligned case.
I didn't know that.
Yeah, and I was just curious about if there's some, how to explain that. But,
well, yeah, no, I haven't done that, but it's worth worth looking at looking if it's close to the criterion,
Right.
and seeing if it
I believe that
makes
all.
sense.
Right, definitely.
It's ITC.
Yeah, no, it becomes harder in the disks around black holes because they behave less like a rigid plate, and they're more likely just to warp and twist.
Right, exactly. But that also made me think about, are there any, I guess in this case the mass ratio is pretty extreme. What is it, 1 to 100? Or
1 to 10.
1 to 10? I guess it's not that extreme, but would you expect any illumination from the secondary and warping of or misalignment of the secondary disk?
Yeah, so that is something we're looking into now. So even though they behave a lot like rigid plates, you'll still get some warping, right? Because there is a misaligned torque.
Yeah.
And a lot of these scattered light images, as well as showing the huge shadows, also show some evidence for spirals imprinted on the outer disk.
Okay.
Right, so
But that could be caused by the temperature differential.
So that could be temperature differential, or it could be scattering, shadowing from
the second guy.
Yeah,
that's pretty cool.
So that's something we're looking at. And they all show, the ones that show this misalignment do all show this sort of indication of spirals.
Yeah. Okay. So yeah, it's interesting. 10 to 1. So I have a paper where we talk about mass ratios where you expect this inner and outer disk ratio to change.
Thank you. Sorry, let me interrupt. Just got to say thank you. Right. It's very interesting.
Thanks very much.
Don't drop your laptop. Right. Okay.
Is this for stellar disks or for?
For just two-dimensional disks around the binary in general. Just looking at the response from small to big mass ratios. But okay.
No. I didn't know that from the Chris Nixon simulations. I know they have their simulations of the broken disks.
Right. Well, this is it's just. I don't think I ever wrote about it. It's just you can see it in the pictures. So, yes.
So it's really that last talk kind of like was. Do you have a moment? Yeah. Yeah. It's interesting because I mean, we know that doesn't at the same time, it does seem like there's not much diversity in stellar mass for TNG. I'm kind of surprised by that. It's like the black hole turns on, it's just like it's a very specific kind of it's strong. The black hole feedback. I don't know how exactly, but how much stronger it is. Okay, good.
Yeah, it's like getting kicks off and then just.
But I mean, here, it's hard to see. I mean, illustrious is like super strong.